Welcome to this course about rational horizon diagram. So before we start with the rational horizon diagram, let's start with observer centric system. So it simply means that we are observing something where the observer is at the center. So imagine that this is our celestial sphere and this is the observer, and the celestial sphere looks like an inverted bowl. So it simply means that this bowl can be part of a big sphere of radius infinite. So that is called celestial sphere. So here we consider observer here at the center. So the point which is directly above the observer is called zenith of the observer, and the point which is diametrically opposite to observer's zenith is called observer's nadir. By the way, I am using the term observer's zenith and observer's nadir. It simply means that as the position of observer is changing, the position of zenith and nadir will also change. So for a particular observer, this is observer's zenith and this is observer's nadir. Now we are having a great circle which is passing through the center of the sphere, that is rational horizon, and it is 90 degree away from zenith and 90 degree away from nadir. So basically, if you remember that this is your earth, this is your equator, and these are the meridians. Similarly, here this is your rational horizon, this is your zenith, and this is your nadir, and there are vertical circles. The definition of vertical circle is the circle which passes through observer's zenith and also observer's nadir. And obviously these vertical circles are going to meet rational horizon at 90 degree. Alright, let's move on to the rational horizon diagram now. So imagine that this is rational horizon. Of course, you cannot reach to the rational horizon, you can only observe from the surface of earth, but for sake of simplicity, that this is your rational horizon and these are the direction: north, south, east and west. And suppose the observer was here. So the point which is directly above the observer is zenith. Now how to represent this three-dimensional picture to a two-dimensional way? So here we are having this vertical circle. I represent this with simply this line. Alright, let me just show it here. So this is north, z and south. This is part of the vertical circle. This is represented as north, z and s. Now moving on, we are having these two points, east and west. So we are having this east, z and west, east, z and west. This is another circle. So in this rational horizon diagram, we are showing this NZS, that is the prime vertical circle. Sorry, this is principal vertical circle, this fellow, and this fellow is prime vertical circle. By the way, in this rational horizon diagram, all the arms are 90 degree. If you see carefully, from this position to this position, the angular measurement is 90 degree, and here also angular measurement is 90 degree. Similarly, we can say that all the four sides of this rational horizon diagrams are of 90 degree in angular measurement. Now we need to understand a term, true altitude and zenith distance. So this is your rational horizon diagram, and suppose this is the body. So if anything we measure from the rational horizon diagram to the celestial body, that is the true altitude. So this is true altitude. How it is going to be represented? Suppose this body is here or here or here, wherever. So this distance or this distance is the true altitude of the body. Now this distance is zenith distance. The zenith distance is from zenith to the celestial body, and true altitude is from rational horizon to the celestial body. Obviously, here the true altitude is 0 and here the true altitude is 90 degree. And you should also know the relationship between zenith distance and true altitude. That means total is 90 degree. So in the simplified way, again I am showing here, this is the true altitude, this angle, and this angle is zenith distance. Zenith distance. Alright, so how it has to be shown here? This is the true altitude here, this is the true altitude, and this is zenith distance, this is zenith distance. Now moving on to another concept, elevated and depressed pole. Well, if you are considering the Earth by the way rotates like this, so we'll see the celestial sphere is going to rotate in opposite direction. By the way, Earth appears to be rotating west to east, so celestial sphere has to appear rotating east to west. And if this is the rational horizon, then obviously, and you are cutting the rational horizon, this diagram from the rational horizon, then obviously we will see that one pole is above the horizon. So in this case, north celestial pole is above the horizon, and obviously if this north is above the horizon, this is below the horizon. So here the south pole is below the horizon. So any pole which is above the horizon is called elevated pole, and the pole which is below the horizon is called depressed pole. Then how to represent? Suppose this north pole is above the pole, so this is the so north pole is above the horizon, so here this is the horizon, so here you can see the north pole, and obviously south pole cannot see, you cannot see south pole here. This is a quick revision. So we need to talk about equinoctial as well. Well, equinoctial is nothing but the projection of equator. Basically, you can see celestial equator or the equator. So on the Earth, surface of Earth, suppose this is the Earth here, this is the equator, and all the parallels of latitudes are measured north or south of the equator. Similarly, if this is the equator and equator is projected here, that is equinoctial. Now, how to represent this with the red color? This is your equinoctial. Alright. Now, look at the equator. Suppose this is the equator and this is the parallel of latitude. So, this angular distance is latitude of the place. Similarly, if this is the equinoctial and this is the observer, obviously, this measurement is the latitude. So, this is latitude, and obviously this latitude is north, because here the elevated pole is north pole. South pole is not visible in this diagram. And from equator to pole is 90 degree, you know it very well. So from equinoctial to celestial pole is also 90 degree, and this is your latitude. So obviously this PZ is 90 degree minus latitude. Now we come to another important term, and which will be used very frequently, that is the declination of a celestial body. Well, the declination is like the latitude of a place on the surface of Earth. So on the celestial sphere we call it declination, and declination belongs to celestial body. Imagine the sun is rising like this in the east, crosses the observer's meridian and sets here in the west. So this is the daily motion of the sun, east crossing the zenith or crossing the observer's meridian and setting west. By the way, these natural events are called, this is rising, when the sun is rising here in the east, and this is setting when the sun is here at the west, and when it is crossing meridian passage, that is called noon. So the declination is like you are having the equinoctial here. So anything which is 0 degree, which is north or south of the equinoctial, that's the angular distance, that is called declination. So in this case, here the declination is north, and this distance from 0 degree to here, let me I think mark here, that is, this is the declination of the body. And what is going to be the daily motion? Suppose the body is sun here, the sun is going to rise like this, it is going to move, there will be meridian passage, and sun is going to set like this. By the way, this is the scenario when the declination of the sun is north. Then you should know, if the declination of the sun is south, obviously this is your equinoctial, and anything angular distance south of this is south declination. And now the sun is going to move, the daily motion will be like this, and like this. Alright. So we need to understand more about declination of sun, why it's changed, because it depends on the tilt of the Earth's axis, which is 23.44 degree. So let's talk about a very important term, plane of ecliptic. Well, all the planets and sun, suppose this is sun and these are other planets, Mercury, Venus, Earth, Mars, asteroid, Jupiter, Saturn, Neptune, they all lie in same plane, and that plane is called plane of ecliptic, or you can also say this is the plane of Earth's orbit around the sun. So this is the sun and this is Earth. This is also the plane of Earth orbit around sun, and this is also the plane of all other planets around the sun. Then we need to understand the term obliquity of ecliptic. Well, this is the angle between equator and ecliptic, and that is how we are going to depict this on the next picture. Suppose Earth's orbit here is here, and we call it as horizontal. Obviously 90 degree to that will be vertical. Let me name it as vertical. So Earth's axis of rotation is this one, and this is going to make an angle of 23.4 degree. So here also this is the equator, it is also going to make an angle of 23.44 degree to be more precise. So this angle is called obliquity of ecliptic. Alright. We need to understand more. The Earth is going to rotate around the sun like this. And these are 4 positions. So when the Earth is here, the sun is on the right hand side. Similarly, when the sun is here, Earth is going to be like this. Now the Earth moves at point number 2. The sun also going to move at point number 2. The Earth is going to move like this. The sun is also going to move like this, apparent motion. So this is the real motion on the left side, and this is the apparent motion of the sun. By the way, as the Earth is going to rotate like this around the sun will also appear to be rotating around the Earth in an elliptical orbit. And this motion can be explained here. Suppose sometimes sun is here, sometimes sun is here, sometimes sun is here, sometimes sun is here. So here at point number 1 is summer solstice. Here the declination of the sun will be 23.44 degree north. The declination depends on the obliquity of ecliptic, just now we have studied. And here the declination of the sun will be 0. Then the declination of sun start moving, then it goes to south. And here the winter solstice, the sun's declination will be 23.44 degrees south. And I have now again start reducing, and then again it becomes 0. By the way, these points where from south it becomes north, and at some point it becomes 0, that is called first point of Aries. and when it was south and then moving and it was north, then it became south, and at some point it became 0. That is called first point of Libra. All right. So this is the annual motion of sun. This we can call it apparent annual motion of sun. By the way, daily motion will be like this. So when the sun's declination is north, sun is going to rotate like this. When the sun's declination is here 0, sun is going to rotate like this. Then sun's declination is south, sun is going to move like this. Daily motion. Then sun will go up. That is how the sun's movement will take place. All right. Then we need to understand one more term, which is local hour angle, LHA. Well, 360 degree of rotation is taken as 24 hours. So obviously 15 degrees 1 hour. So all these meridians on this celestial sphere are called hour circle. All right. Then hour angle is the angular distance between two planes of celestial meridians. Suppose one celestial meridian is passing through the observer, another celestial meridian is passing through the celestial body. Then this angular measurement is LHA. So the definition of local hour angle is westerly hour angle measured from observer to celestial body, and it is expressed from 0 to 360 degree. This one, and it is measured westerly. Why? Because Earth is rotating west to east. If seen from top, obviously the celestial sphere appears to be moving in opposite direction. All right. So rotation of Earth is west to east, and this is anti-clockwise. If you see from north or from top, the celestial sphere appears to be rotating east to west. Now coming back to other definition, Greenwich hour angle. If you measure this from G, that becomes Greenwich hour angle, and if you measure from first point of Aries, it becomes SHA, sidereal hour angle. If you measured from Greenwich meridian, then it is considered as Greenwich hour angle. If you measure from local observer, it becomes local hour angle. So I hope the definitions are pretty clear. Westerly hour angle measured from observer to celestial body in anti-clockwise direction. This is measured 0 to 360 degree in this direction. That's a clockwise direction from the top. So we need to talk about another term which is called azimuth. Basically, azimuth is the bearing of a celestial body. So if you see this diagram PZX, this is PZX triangle, typical PZX triangle which is formed in rational horizon diagram. So here the angle Z is azimuth. You can express azimuth as three-figure notation. Here this is 00 degree, this is 090 degree, this is 180, 270, again this 360 in clockwise direction. All right. It can also be expressed as quadrantal notation also. Like for example, something is here, then it can be expressed as north, xx degree, whatever east, and so on. Now let's talk about some examples. Suppose latitude is 40 degree north. So here we need to show the north pole here, and you need to mark WQE, which you have marked here. So the Q to Z is 40 degree. Obviously all the arms are 90 degree. If it is 40 degree, this is going to be 90 degree. This is 40 degree. And the declination is 20 degree north. So this is 40 degree. The declination here is 20 degree north. So the motion of the sun will be like this at some point, or the celestial body will be like this. So at some point, suppose it is here. So this angle is zenith distance, and this is PZX triangle, and obviously LHA is this one, and this LHA is suppose this is angle P, the LHA will be 360 degree minus P, the BD will be on the eastward side, and the time will be AM, it will be before noon. That is how we can express. Then we have this example 2, the body from here, it has come here, obviously this is your LHA. So the P will be equal to LHA, the time is PM, the body is in the westerly direction, and this is again PZX triangle, and here this angle here, actually this angle is azimuth, but this is expressed like this. Alright, now let's move to another example. Latitude 40 degree north and declination 20 degree south. So this is 40 degree north because all the measurement is taken from the Q to the up or Q to down below. So Q is equinoctial, that is 0 degree. So the body is going to move like this. So obviously this is your azimuth and this is your PZX triangle. And the LHA will be this one from observer, and this is angle P. So LHA will be 360 degree minus P, the body will be in the easterly direction. Now let's talk about example 4, which means latitude 40 degrees south, declination 20 degrees south. So everything is south, so we have to show the southern pole here. If the southern pole here, then we show the equinoctial like this, and from equator down below, this is 40 degrees south and this is 20 degrees south. Obviously here the LHA will be in this direction now, and this will be the angle P. So LHA will be 360 degree minus P, the body will be in the easterly direction. Alright, so you need to understand, if you see from south pole, it will be looking like this. Then we have the last example. This is 40 degrees south and declination is 20 degree north. So 40 degrees south, obviously this is Q, this is 40 degrees south and 20 degree north, so you go up. So body is going to move like this, sun's declination will be like this, and the LHA will be like this here. Here the south pole is the elevated pole.